Good morning. This is Mike McGinn, your online instructor for NetI 105, and we are going to talk today about Chapter 4, Routing Concepts. Well, why do we route? Well, routing is, or routers, or layer 3 devices are used to basically make determinations as to where to send a packet if the destination IP is not on the local area network of the device that sent the packet. So in other words, if PC1 wants to send a packet to PC2, but those two PCs are not on the same local area network, then we need some sort of a device that says, okay, I see where you want to go. Let me take you and send you on your way so you can get where you want to go. I put that very simplistically, but in essence, that's all a router does. Of course, we'll make it seem a lot more complicated as our discussion continues, but in its simplest terms, that's basically what a router does for you. A router is just like any other computer. It's got a CPU and an operating system and has different types of RAM, which we'll go into here because you'll be tested on this. Random access memory, which is volatile RAM. In other words, it clears when the device is powered off. It contains your running IOS, your running configuration, various dynamic tables such as your IP routing table, your Ethernet ARP table, and your buffers for packet processing. So that's what RAM is. It's kind of like the stuff that it needs to actually work while it's working. Read-only memory provides permanent storage for boot up instructions, diagnostics, and also limited IOS in case the router cannot load the full-featured IOS. ROM is firmware essentially and is referred to as non-volatile because it does not lose its contents when the device is powered up. Non-volatile RAM is kind of like user-defined non-volatile storage. Non-volatile because it does not clear when it's powered off. And this is where you're going to find your permanent storage for startup configurations and other system files that you want to may want to put on there. Flash is also permanent storage, and it contains the actual IOS for the router that is used when the computer boots up. This is where it gets its copy to put into RAM during the boot up process. Flash is non-volatile, of course, and it does lose its contents when it is turned off. So in reality, what you'll see is typical topology is you got a couple of different local area networks, and you have some sort of wide area network. That could be a private wide area network where you have a company and this is location A and this is location B, and you just want to get traffic from A to B. So what routers do is they direct packets to the proper destinations, and also they can connect different media. For example, this connection here could be a serialized, a serial T1 connection, whereas these can be Ethernet. So what a router does is it does two things basically. It determines the best path to send packets, and then it goes ahead and forwards those packets toward their destination. Routers use a routing table to determine the best path to use to forward a packet. So when a router receives a packet, it examines the destination of the packet and uses the routing table to search for the best path to that network. Now in this illustration here, that's not too complex of an operation because as they show, there is only one, for router R1, there's only one place to send it, which is to router 2. So any packet that is destined for any network that is not on the 192.168.1.0 network is going to go to router 1. Router 1 has a entry in its routing table that says, in essence, any packet that isn't on the 192.168.1.0 network, go ahead and send it to R2. And then R2 forwards it on to the destination IP in this illustration. There are some packet forwarding mechanisms that you need to know. There's three. And what we mean by packet forwarding mechanisms is how does the router actually process the packet as it ingresses and egresses out of the router. And they talk about three different ones: process switching, fast switching, and express forwarding, Cisco Express Forwarding, or CEF. Process switching is pretty much an obsolete technology. It's the way early routers worked, where every time a packet came in, the CPU woke up and it examined the packet and then looked it up in a routing table and then went ahead and forwarded it. This works very well, but it is very slow in that it puts a lot of load on the CPU. So if you've got a lot of packets traversing a router, this could be pretty inefficient. Fast switching is another better mechanism which uses what is called a fast switching cache to store next hop information. So when a packet arrives at an interface, it's forwarded to the control plane where the CPU searches for the match in the fast switching cache. If it's not there, it is process switched, as we discussed previously, where it actually looks it up in the routing table and then forwards it to the exit interface. But if it's seen that destination address before, it keeps where it needs to send it in its fast switching cache. This next hop information in the cache is reused and reused without CPU intervention from that point forward. So it doesn't have to do lookups, which is essentially a query of the routing table for every single packet that it sees. If it's seen that destination network before, it will put it in a memory cache so that it can forward it on with less CPU intervention. Cisco Express Forwarding is the preferred in the Cisco world. It's Cisco iOS packet forwarding mechanism. And like fast switching, it does build what is called a forwarding information base and an adjacency table. The difference here is that the table entries are not packet triggered like fast switching, but change triggered, such as when something changes in the overall network topology, in other words, in its adjacent routers. Therefore, when a network is converged, that fib table contains all the information the router would have to consider when forwarding a packet. So it's got reverse lookups, next hop information, routes, including the layer 2 information, and this makes it the fastest forwarding mechanism and is preferred on Cisco routers. So in this slide here on 4116, it kind of illustrates very feebly the differences between the two. So this is something you need to know so you can answer correctly on any questions that come through this. So here's a common analogy that's used to describe the three packet forwarding. It's on the bottom of the slide, so that's something you might want to read so that you get a better understanding of what process switching or what packet forwarding mechanisms are all about. So I've got a couple activities here. There's a packet tracer on using traceroute. Traceroute is a nice utility that tells you how your packet has traversed to get to its destination. In other words, the number of hops. Hops are basically how many routers or layer 3 devices has a packet had to traverse in order to get to its destination. And traceroute basically tells you that. So if you want to know, if you want to send a traceroute to some website somewhere, you'll get a list of all the up to 30 routers that it has traversed in an effort to get to its destination. Slide 4.1.2.1 does a nice job of kind of showing you where routers fit into a real world situation. You know, you've got a home office, central office, and branch office. In the home office, you know, you have your internet router, something you guys all probably have, and it connects to the internet, and what that router does is it says, hey, if it's not destined for any of these devices in my home office, then send it on to the internet and let it try to figure it out. And that's exactly what happens. Uh, so central office, similarly, any traffic that's not destined for its local area network, it will send it to the router, and the router will make a determination as to whether it's a private wide area network IP address, of which it would go up to its private cloud, or it would just send it on to the internet, and also similarly for branch offices. So you've got 3 routers here that are managing all the traffic between the local area network and any other destination network that it needs to work with. Also note that the home office can also get to the cloud, but the path might be for it to go to the internet, which it is via the internet to get to the central office router and then get relayed up to the cloud that way. This way the organization doesn't have to have routers and private cloud connections at every location. Only locations that have an adequate number of users would have direct cloud connections, but the home office may have an indirect cloud connection. Default gateway is really important. Default gateway is essentially the IP address. You have it on your computer that says, okay, if a destination IP, if I need to send a packet to some place that's not on my local area network, where do I send this packet so I can figure out where to go next? And that is your default gateway. In your home, it is the internet router. So when you type in a URL for a website, as an example, www.amazon.com, through DNS, it translates that into an IP address, and it determines that that source IP address is not on your network. And so it forwards that request to that website to the default gateway, which then ultimately forwards it on and ends up at an Amazon.com server where it will fulfill your request. So here's an example of how the network scheme in a wide area network would work where routers are involved. In this scenario, you've got a local area network here. You've got a default gateway. You've got a wide area network. You've got a default gateway for this local area network. And each of those networks has some sort of IP network scheme. So this is an IP4 network, a 1.0/24, a 2.0/24, and a 3.0/24. So the inside interface for the 1.0 network is 192.168.1.1. So that is the default gateway for this local area network. So if you were to do an IP config or check the IP status on this PC, you would see that it has an IP address of 192.168.1.10 and its default gateway is 192.168.1.1. Then the outside interface of the router, which is the interface that faces the outside of the local area network, it will have an IP address assigned to it, and then it will have a default gateway to 192.168.2.2, which is the outside interface of that router in this scenario. Then, of course, the local area network of this network is the 3.0 network, so the inside interface, as logic would dictate, would be the 3.1 IP address, and the PCO, of course, has got the 3.10 with its default gateway as the 3.1. So topology diagrams and addressing tables, you'll see a lot of these in the packet tracers and exercises that we do. So being able to look at this and be able to visualize this is going to be really important. So they go through here and they show you how you can statically assign an IP address to a PC. I'm sure that you guys have done this before, but if you need a review, this is a good slide for you. And then, of course, they talk about LEDs, and I don't think you're tested on LEDs, but this is good to know if you ever work on physical equipment. Console access, very similar to accessing a switch, which you've learned. You need a console cable, some sort of a terminal emulation software, Teraterm, PuTTY, Hyperterminal, etc. And you basically access it the same way. Then we get into enabling an IP on a switch, and kind of reviews that, where you go into VLAN 1 and you set its default gateway to the router, which would be the inside interface of R1. So 192.168.10.1, this switch is on a 10.0 network. IP address of the default gateway is 10.1, so getting that device in there basically allows you to communicate from that switch to other devices across the wide area network if you need to do that. So that's something you need to know. So we get into configuring basic router settings, and I'm not going to go through this in detail because we have packet tracers that take you through this. But the normal stuff, you want to name your device with the host name command, and then you want to secure management access. You want to configure a banner, that sort of thing. And of course, you want to save your config. And then configuring an interface is important, where you actually go into the interface configuration mode for the interface you want to configure and give it a description, an IP address, which would be, in this case, the inside interface of Ethernet gigabit 00.1, so you're giving it a 10.1 address with the proper mask. No shutdown command is what actually brings that interface up, so if you don't do that no shutdown command, it's not going to come up, and you're not going to be able to communicate with that particular interface on that router. So that's really important not to forget. And then they take you through configuring an IP6 interface as well. Yeah, we can't forget about IP6. And they talk about loopback interfaces. What a loopback interface is, it's a logical interface internal to the router. It is not assigned to a physical port, and therefore never can be connected to any other device. It is considered a software interface that is automatically placed in the upstate as long as the router is functioning. So where this is handy is, using it to test stuff and managing a Cisco iOS device, because it ensures at least one interface will always be available. So it can be used for testing purposes, such as testing internal routing processes and emulating a network that's behind the router. So loopback interfaces, you do interface loopback, give it an IP address, no big deal. Then we go through a list of commands. Show IP interface brief shows you all the interfaces on a router, what their IP assignment is, and what their status. That's really an important one to know. The show IP route command shows you all the routes that are configured in the router. So basically the way you read this is that if a device needs to get to the 192.168.10.11.0 network, it has the routes directly connected to it to get to specific subnetworks within that network, and tells you what Ethernet address to get out. And you've got some packet tracers that are going to take you through this as well. And of course, you can see in the show running config for a specific interface, you can see exactly how it's configured, so they can show you that. Take you through a little couple exercises here. So Um, and then the same thing with IPv6. And the terminal, you can do, it also tells you how you can change the history, terminal history size, or the command buffer of the router. In other words, give you a list of everything you've typed in for a given number of uh, lines, and that's where the size parameter comes in. So that's a good thing to know. It helps you troubleshoot things. The more little shortcuts you know, the better off you're going to be. So encapsulating and decapsulating packets, this goes through the logic that goes on because it's, in essence, you have to get those packets into frames. And so you have a encapsulation, decapsulation process that goes on. So you've got the entire OSI model here that is functioning on the PC, and when it needs to communicate, it creates a packet, and then it goes down the OSI model to get to the media that it has to travel, and then when it gets to that device, it goes up to layer 3 and then goes down, etc. So it's not hard to understand what's going on logically. It's kind of a review of what we talked about in that I-105. So the next few slides do a good job of just illustrating what's going on so that you understand the mechanics of what's going on with the frames and the packets and the MAC addresses and that sort of thing. So this is something you need to go through so that you have a thorough understanding of the processes that are going on. It'll help you in troubleshooting. So nice illustration on 4.2.21 that kind of goes through what the forwarding packets decision process is. It's a good thing to review. And then we start talking about best path determination. And this gets into where you've got multiple routers involved and that you have multiple paths to get to your destination network. Um, Basically what happens is router 1 has multiple routes to get to this network down here that PC2 is connected to. And which one it chooses, it determines based on some sort of a metric that determines which path is the best path if it's available. Um, Now, how routers learn these routes, you can do what is called static routing, which is where you manually put in the routes to the routers that are adjacent to it. This is pretty easy to do, but and if you've got a very small network, this might be the way you want to do it. But in larger networks where you have lots of routers, lots of locations, there are what are called dynamic routing protocols, which basically what happens is all these routers are sending out messages to you, and they're basically received by their adjacent routers. And what's in those messages is information on what networks are connected to that router. So R1 obviously knows about this network, and what it does is it sends messages to any adjacent routers that says, hey, guess what, guys? I have access to this router. And so now router 2 and router 3 know that router 1 can get you to that particular router, and it tells you what kind of link and that sort of thing. And that's how dynamic routing protocol works. You can also do load balancing with routers where you can send packets to a specific destination out multiple interfaces simultaneously where those interfaces have paths to its destination. So you have what is called equal and unequal cost load balancing and that sort of thing. So some pretty interesting stuff. So like I said, it's possible for a router to be configured with multiple routing protocols and static routes. If this occurs, the routing table may have more than one route source for the same destination network. So for example, if you've got RIP and ERGRP configured on a router, which are both dynamic routing protocols, they may learn of the same destination network, but each protocol may decide on different path to reach the destination because they calculate best path differently. So Cisco IOS uses what is known as administrative distance to determine kind of like the priority of which dynamic routing protocol I am going to trust the most. So obviously, if a network is directly connected, it has an administrative distance of 0, and if it's internal BGP, it has an internal distance of 200. So, preferred interfaces based on how those were learned, how those routes were learned, are in an ascending order. So the higher the administrative distance, the less likely you're going to want to use it if you've got a lower one in there. So you're always going to want to use a static route before you use anything else. It's going to assume if you put it in there, you put it in there for a reason. I guess that's a big assumption. But things like internal EIGRP is always going to be chosen over OSPF. And as you can see, there's a lot of different dynamic routing protocols. And yeah, through your journey through the Cisco curriculum, maybe not all in this course, you're actually going to know what all these are and even be able to configure them. Yippee. So what we do in 4312 is we start getting into the routing table and learning based on the code here on the left how that particular route was learned, and know the difference as local route interfaces, directly connected interfaces, static routes, dynamic routing protocols. All this stuff is tells you in the show IP route what's going on with those. And the sources of the routing table entries are identified by the code there, like I said on the left. Here it's a D, which means it was identified dynamically learned network from another router using EIGRP dynamic routing protocol. So it kind of tells you, okay, I know this, and this is how I know, and what method that I learned it. And then you have, basically this graphic here is excellent, and you really need to study this because what it does is it dissects a line on the routing table so that you can actually know what all this means. At first glance, this probably looks like gibberish, but once you understand what each section of this is telling you, it starts to become clearer. So, for example, this first part identifies the destination network. And this part here, you have a number and a slash and a number. And the first number is the administrative distance or trustworthiness of the route source. So this is, since this was learned by EIGRP, it's assigned a 90, okay? And then another metric which can be calculated by EIGRP gives you the metric for the cost that to get to that destination network. And then it then identifies the next hop IP address and identifies the amount of lapse time since the network was discovered, and then the physical interface that it needs to go out of this particular router. So, once you've learned that and committed to memory, looking at routing tables and understanding them should come quite a bit easier. When we talk about static routes, and again, static routes are routes that you manually put in that tells you how you want traffic to be routed. And then, of course, there's a default static route, IP route, all zeros, means that all traffic is going to go to a specific command if there isn't another routing entry for that destination network. It's kind of like if all else fails, send it this way. So that's how a router can be an internet router and also have multiple interfaces to send it to multiple other networks. So routers can have many, many interfaces. So this, for example, router 2 has 3 interfaces on it. And so the default route for router 2 is to send it out to the internet. But then there's going to be routing table entries that's going to tell it about the other 3 networks. I'm going to give you some examples of a static route. A static route is always an S. And then they talk about dynamic routing protocols a little bit more, and EIGRP and OSPF, ISIS, RIP or RIP. So they go through some explanation of what those are, but basically they're just different ways that routers learn about each other. And there's advantages and disadvantages to them. Some are low overhead, but they converge slowly if there's a change in the network. Some are very high overhead, but have short convergence times, and that's basically the trade-off. And when I mean convergence, it's like when something changes in the network. For example, you replace router 2 with a different router, or maybe you add a network to router 2 through another interface. Then what happens is when that comes up, it's sending messages throughout the network, and it has to converge. Conversely, if you've got a network that has multiple paths, um, if one router goes down, then it has to update all the adjacent routers are made aware that that router is down, and then it updates any of its adjacent routers that they no longer have that path, and so therefore that's how convergence happens. So how fast that ripple effect rolls out has a lot to do with what kind of routing protocol you have. So they talk about what type of IP routing protocols are supported for IP version 4, IP version 6, etc. And that takes us through chapter 4. So chapter 4 is a fun chapter because it really makes you understand how the internet really works, in my opinion, or how interconnected networks really work. It kind of fills in the fuzziness, I think. So spend some time on this. Do the packet tracers that are assigned, and I encourage you to do the packet tracers that aren't assigned, because it just reinforces your learning and makes this a better overall learning experience for you. So that's it, and then here in a week or so I will get an overview for chapter 5 out. So enjoy your week. Good luck on your assignments and your exams that are coming up. Take care.